So welcome back, everybody. So as of yesterday, we went public with the national version of this course in the sense of advertising it to as broadly as we could. So it'll start on February 14th, all the lectures from spring 2012. So at that point, there might be some bandwidth sharing with the Q&A for the teaching assistants, but we'll see how that scales up. So anyway, are there any questions about last time's lecture before I continue? So my goal today is to finish lecture 3. I only got through the middle of it. And that was talking about parallel computing, in particular comparing programming models to machine models. So programming models is how you actually express parallelism, how you express the fact that these processors have to synchronize with one another, they have to share data. And we started, and we only got through shared memory, and we explained how to write a very simple program that summed up a bunch of numbers. And so now that I've done that, I'm going to go off and talk about the machine models, the hardware that actually implements that, and a little bit about what the costs are of all the things that you have to do. And then I'll move my way down through these other kinds of ones. So shared memory, that's basically the multi-core chip on your laptop. Distributed memory are the big machines like Hopper, in which you're going to be doing your homework, and there's lots of these others as well. So this, hold on. Let me start this again. This is a little munged. Okay, good. Now the slide is here. So in this case, the simplest way you can have a shared memory machine that implements that programming model I told you about the last time is to have all the processors, P1 through Pn, they each have their own little local caches, and they're all connected over a bus, a big wire they all share. And whenever one of those processors says, please read location 37, they will all go to the bus and get to either the shared value of location 37 in the shared cache, $ means cache, or they go to memory if necessary. Right? And so these are called symmetric multiprocessors historically, and many, many companies have built them. And in multi-core chips, which is like in your laptop, they're there too, except there it may be that all the caches are shared instead of having some shared and some local. So one nice thing about the programming model here is that it's called uniform memory access. So that whatever you go get a remote piece of data, whenever anybody does, it all costs the same going over the bus. Right? So you don't have to think so hard about what's local and what's remote, although obviously it's faster to get the stuff that's in your local cache. Now the trouble with this is sort of the simplest programming model. This is why people built it originally, but it's very hard to scale up to very many processors. It's typically limited, 32, maybe people are trying to build 64 that look this way, because there's a bottleneck, which is that everybody is sharing this one common hardware resource, and that gets to be a problem. And the reason is that all of these caches here need to be kept coherent. Suppose this guy loads location 37, and this guy loads location 37. They can keep reading it, and it's very cheap. But what if one of them writes it? Right? The other guy who has a copy has to find out so that they have a consistent copy. That's called cache coherency. And so if everybody starts touching shared data like that, you're going to have an enormous amount of traffic over that bus, and that's why it doesn't scale up. So let me just run a little experiment here. This is taking a climate code, a very simple climate called a shallow water model, and running it in the most embarrassingly possible parallel way. I'll have the data on the next slide. So all I'm going to do is take a bunch of copies of it, and each processor is going to be running its own subset of the data. In fact, it's just the copy of the same program. And I'm going to scale it up so it doesn't fit in cache anymore. And I'm going to ask, how fast does it run? So this is the simplest kind of program you can imagine. Everybody's running independently. They don't share anything, allegedly. And so hopefully if you double the number of processors, you should also double the speed. And so that's an experiment that we can run. But what we'll see is that actually it doesn't scale, because they're all eventually sharing that bus. Even though they're not trying to share data, they're all trying to get to memory to get to stuff that doesn't fit in their local caches. So let's just see what the data tells us. And so here is a plot. The horizontal axis is the size of the data set. It's the resolution, horizontal resolution of the climate model. So as you go to this side, it's bigger and bigger. The vertical axis is the speed per processor. So if everything were perfect, no matter how many processors I used, 1 or 8 or 16, it would all be the same performance, right, per processor. I would just get perfect speed up. And here, when I have a very small problem that kind of fits in cache, when I go from 1 to 8 to 16 to 24, I get about the same speed per processor. So it is scaling perfectly well because there's no shared traffic over the bus. But when I get up here to the really biggest problem, and all of these codes are sort of just going through all the data, and over again, the data does not fit in their local cache. That means they have to go out through over the shared bus to get to memory to do it. And now, as I increase the number of processors going over that shared bus, it slows down per processor. So it no longer helps to have this kind of architecture. And so that's a limit to this. So it's perfectly good in maybe the small scale machines on your laptop, but it's not going to get us to high performance computing. So here's the next machine model that people tried to build to address this problem. And again, there are a bunch of shared processes. And so from the programmer's point of view, it kind of looks like just the way I did before. So you have shared variables and private variables, and you might have locks. But now, you don't assign a program to a processor, and it gets that processor, and it just owns it for a while. Basically, all the hardware is shared. And so now what you have is that the one process can have, for example, 8 threads running on each core. So you could have a total of 64 threads, programs running on 8 cores. And so each thread now has a choice of 8 different things it can do at the same time. So why is that a good idea? Suppose it's running one of those threads and it's all running very fast, but now suddenly it accesses memory. That one thread goes off and says, please read something, go over the bus, it'll be slow. What that hardware can do in one cycle is issue the memory instruction for that first thread, and then go get the second thread and start doing it. And then they can run it. So while the first thread is waiting for its memory access, the second one can be doing arithmetic or doing something fast. And in principle, all 8 of them could be waiting for slow memory traffic, but probably not. Probably one of them can do some useful arithmetic while the other ones are waiting. And so this is called a multi-threaded processor. And here's some examples. The Sun Niagara, which is a fairly recent commercial machine, did this. And older ones, the Cray MTA and the El Dorado. And so you have all these threads. The processor can shift between them in one cycle. And they all share like the floating point units, the cache, and so forth, and then the memory. And so these machines have been tried. And so here's kind of an example of how your program might map to the hardware. So in this case, imagine I have 4 different tasks, color-coded. This guy's a sequential task. This guy has n tasks of about the same size and then one other one. This guy has 2 tasks. This guy has n. And I have 4 cores. So what could happen and each core can run, say, 16 different threads at the same time. So for example, you may have red processes. Those are subsets of process 1 spread out over all of these machines. You might have the 2 yellow ones from process 2 just occupying that piece of the hardware and distributed any way you want. And as soon as one of these threads becomes waiting for memory, it can go execute a different one. So and the hardware hides that all from you. You don't have to think about it. The hardware does it for you automatically. This makes the hardware a lot more complicated, you can imagine, but it also simplifies writing certain kinds of very irregular programs where it's very hard to imagine how to lay out the data ahead of time so that everybody is only accessing local stuff and everybody is load balanced. So this is sort of the second attempt to make shared memory easily available. And so here is the third and maybe the most scalable one. People got this up to 512 processors. I think that's the biggest machine people built. And SGI is sort of the canonical example of this, plus some research machines. And so the memory is all logically shared, so this kind of looks the way it did before, but it's physically distributed. And what you have is a whole bunch of sort of special information lying around, some tables that say which memory location which address is stored where, and who has a copy of it. So in other words, if each processor has a copy of location 37, because they're all sharing it, and one guy writes it, then that act of writing will update this table, which says that, oh, now only one processor has the most recent version of address 37. Everybody else is out of date. And so when everybody else then goes later and reads location 37, they'll go to that table and say, uh-oh, my information is out of date. And then, only then will they realize they have to go to memory and get that information. And so this is a lot more hardware thrown at that coherency problem, but it does scale up a little bit better. People have gotten it up to 512. Okay, but you can still, obviously it doesn't help you if your problem is sharing too much. It won't make communication costs go away. So, and the network is not a bus anymore. The network, because that was a problem in the general shared memory machine, this can be a much more scalable thing, and people typically build, for example, toruses, where you just have you're connected to your north, south, east, and west neighbors, and all of these tables keeping track of who owns what are connected in this torus. And we'll have a later lecture on what networks look like and which ones are good and which ones are bad. So that's the third memory model that tries to make shared memory available to you. So that's all I wanted to say about shared memory. And now I want to go on to the one that actually does scale up to arbitrary number of machines, processors, and that's the way Hopper is built and many other platforms. It's called message passing. So now I'm going to go back to the programming model and say what it looks like to write programs in it, and then I'll talk about the hardware. But this model is sort of designed for the case where there is no shared memory. So you have a whole bunch of separate processors that are often fixed at when you write your programs. You say, please call 64 copies or 1,000,000 copies of this subroutine. Okay? And you can think of each copy of that subroutine getting executed in a different processor. And so each one of those is going to execute all by itself. It's like writing a sequential. You have 64 different sequential programs that are all running. All their data is local. So here's, for example, I have n+1 processors, and if I have a local variable I on this guy, it's always private. If I have a local variable s, which is that summation variable from last time, everybody's data is private. There is no shared memory. And so you have to divide up your program so that, that they're all going to run independently. And so the question is, how do you ever agree on something so that you could, for example, compute a sum of numbers if there is no hardware shared memory? And the answer is you have to send messages to other people in order to communicate. And so there's a special library, which is called MPI, Message Passing Interface. And so let's suppose, let me just give you an example. Let's suppose processor 1 needs to get information from processor n. It needs to get his partial sum, because they're all trying to compute the global sum of all the s's. Then what processor n has to do is call a subroutine, which is basically put something in the mail. So he says, please send my value of s to processor 1. So you put s in the envelope and put p1 on the outside. And then processor 1 has to execute another subroutine called receive, which means please go to the mailbox and see if anything's there. And if something has arrived from processor n, I'll take it and I'll call the variable s that arrived. And I'll do whatever I want with that. And so for every communication, you need to have these sort of paired up send subroutine calls and receive subroutine calls. That's sort of the simplest model. And let me add that each of these processes, they don't have to be absolutely identical. For example, you could have a branch at the beginning which says, if I'm processor 1, call subroutine 1. Else, if I'm processor 2, call subroutine 2. So each of these can do completely different things. And so you can write utterly general programs. So that, for example, one guy knows to send and the other guy knows to receive. Right? They don't all have to execute the same code. So let's go look and ask ourselves, yes, question. And let me ask that you use the mic.
How does one processor know what data is stored in all the other ones? How does it know it wants to get data from P whatever?
So you wrote the program, and I'll have an example in the next slide. And so you have to know at some point they have to coordinate and agree that it's time to swap data because you want to compute a global sum of some kind. So you, the clever programmer, has to coordinate all the communication between the different processors. And so here's an example of the simplest one, which is where I want to processor 1 owns A1, processor 2 owns A2, and I want to compute just the sum of those things. So processor 1 will compute f of A1, processor 2 will compute f of A2, and then I want both of them to end up with a sum when I'm done. So the natural thing to do is each one sends their local value to the other processor. So processor 1 sends its value to processor 2, and it receives processor 2's value, and then they add it up. So why is this code possibly buggy? I mean, this sort of captures the spirit of what I was talking about before. So it sort of depends, there's a hint here, kind of depends on the semantics of what send and receive mean, right? Do they act like the telephone system, or do they act like the post office? So in this case, imagine that you both picked up, you and your friend picked up a phone at the same time and called one another simultaneously. You'd both get a busy signal. In this case, you'd get a deadlock, right? So each one would do a send, and nothing would happen, and they'd be stuck waiting. So that would be a problem. On the other hand, if it's like the post office and send is simply putting something into the mailbox and then you go back to work, you'll call send and then you'll return and then you'll call receive, and at that point you'll wait until your other processor's mail arrives in the mailbox and then you'll open it and keep going. So both those kinds of send and receives have been implemented, and they're all available in the different libraries because sometimes you want one and sometimes you want the other. So let me try rewriting this code to avoid that problem. Here's another way to do it. So the first processor does send and then receive, and this guy does receive and then send. So the problem that I had in the up here can't happen. This guy does send first, this guy does receive first, so you're guaranteed there's, nobody's going to get stuck. These first two lines of code will always execute. This guy may have to wait a while until he wakes up and does the receive. And then you do it in the opposite direction. And so that's certainly another way to do it, which would work for either the telephone system or the post office. But clearly, if there are more than two processors, thinking of the right order in which to do all these things so you can share some data is messy. And so you would like to have sends and receives which can accommodate any number of processors, and there's a lot of different patterns of communication. And so people invented, and reinvented these kinds of libraries for a long time, and finally, they all agreed on a standard. So just like the basic linear algebra subroutines was an industry-wide standard, so everybody spelled matrix multiply the same way, here everybody spells send and receive the same way. And there's a big thick manual so that everybody's agreed also on whether, some sends are like the post office, some are like the telephone system. And so you can write portable code, and with high probability, very high probability, if you write a code in MPI today, it will almost certainly run correctly in a few years, no matter what kind of architecture people come out with. So this was, a good thing. On the other hand, it was developed in the mid-1980s based on what architectures looked like then. So in some people's point of view, if you're stuck writing code from a long time ago, then it's going to discourage people trying to innovate, maybe build more interesting hardware and software. But this is the trade-off: portability versus innovation. And so, in fact, there was a quote. So this was from a while ago. I'm not sure how I'm going to program a computer in 10 years, but I'm sure I'm going to use MPI. So this is if you like, a pun on a much older quote about 30 years ago where somebody said, I don't know what language I'm going to be writing in 30 years, but it'll be called Fortran. So no, they weren't absolutely right, obviously, but nonetheless, this is what people sometimes buy into in order to guarantee that they're going to invest a lot of money in building software and they want it to run for a long time. And they come up with standards. Okay. So this is, and we will have a lecture on the details of MPI later, well, some of the details, so that you can actually do one of your programming assignments in this particular format. And there's tons of online documentation, too. So that's the programming model. So now I want to talk about the machines that people built that go with it. And as I mentioned, Hopper, the Cray XE6 that you're going to be programming on, works. This goes back an awfully long way. These are some historical machines that people built. These were PC clusters. You went out to the local store, you bought a bunch of PCs, and you connected them on a network that you bought at the same store. It was sort of like the poor man's way of building supercomputers, and that was actually a bit of a revolution, that people realized, I can build a large parallel machine very, very cheaply just by building it out of commodity parts. And so, so this, I'll have one more slide of that history in a moment. But there are lots of other machines. Franklin was Hopper's predecessor, various IBM machines. These are older parallel machines we used to have here in the department. These are all distributed memory machines, but the new ones, each individual node is a shared memory machine. In other words, Hopper may consist of zillions of distributed memory machines you call MPI, but if you look inside each one, it's a multi-core chip. So I'm sort of hiding the fact that these machines are actually hybrids. They're a hierarchy of distributed at the top and shared at the bottom, but I'll come back to that later. So each processor has its own memory. So here's a picture. Each processor has its own memory that it can refer to. And then they're all connected by this interconnect. It's not a bus anymore. It's you're just connected maybe to your 4 neighbors or your 6 neighbors. I'll talk about that later. But there's a new piece of hardware people have put in to make it run faster, and that's called a network interface, or a special network interface chip. So you can think of this as the post office. So when this processor wants to call a send or a receive, it doesn't have to do it all that work by itself. It doesn't have to wait for a long time for its neighbor to fill up the memory, to put something in the mailbox, the network interface chip is a separate processor that does that all for you. So it's the one that packs and unpacks the mailbox, that sends things over the network, and that does the waiting when necessary for something to arrive. In the meantime, the processor can just keep going full speed ahead, unless it absolutely has to wait for a message to arrive. So here is this one of the two big projects that set off this revolution. It was called Beowulf, and that's a picture of Tom Sterling, who had the idea of just go buy a bunch of PCs at the local store, and then you buy an internet at the local store and put them all together. And people realized how cost-effective it was just to buy off-the-shelf parts to build your own machine. And in fact, that was sort of the beginning of the end, temporarily, of these special-purpose supercomputers, because people realized they could just build them themselves. They didn't have to go buy special-purpose hardware from a company like Cray. And so a lot of people did this, worked on it for a while, and there were standards, and this was all a good idea. So, but it didn't completely take over. I mean, actually, 80% of the machines on the top 500 are clusters. So it still is kind of a dominant architecture in that way. But companies that do special purpose stuff have come back for reasons I'll talk about later. So here is another distributed kind of memory machine. And if you've ever seen the movie Contact with Jodie Foster, where they're looking for aliens, it's sort of the intellectual history of that is this kind of computing. So there's a program called SETI at Home, which takes signals from radio telescopes around the world, and you can sign up your PC to say, I want to look for an alien. And what you will do is it will mail you automatically a subset of some radio telescope signal after it subtracts out some noise from the Milky Way. And then you will run a program and look for signals. You'll do some signal processing and send it back. And 3.3 million computers around the world have signed up to actively look for aliens with 1.3 million users. At least that's what the website said yesterday. So this is like one of the largest parallel computers in the world. It's not doing just looking for aliens. It's been used for protein folding and chemistry and mathematics, looking for huge primes. And you can sort of go to these places and sign up any project you want. You can go through a long list and say, I want to have my laptop battery drained doing this one, or you can invent your own and put it there. And so this is all very, communication is incredibly expensive. It's all happening over the internet. And so, what they have to do is send you something, a subtask that's embarrassingly parallel, and you get to work on it for a long time before you send it back. And so the other thing that you have to worry about in this environment is trusting the person at the other end of the link. And so what they do is that for every piece of data, they send it out 3 times. They don't just send out each piece of radio telescope data once, they send it out 3 times. One reason is that somebody's machine may break and never send it back. And the other reason is somebody may want the publicity and say, I found an alien, right? And so, but 3 people have to agree on that, that they found aliens. Only then will they go look at the data. So there's a lot of reliability and redundancy problems when you build really big machines, and that's going to come back at the exascale level too, not because of trust, but because of things failing. Okay. And let me say that if you go to BOINC, which is the Berkeley Open Infrastructure for Network Computing, you can find their website, all of these different activities. Okay, so now I'm going to go back to programming models now, and this is sort of a blend between distributed memory and shared memory. It's trying to give you the illusion of a shared memory machine, even though you're programming on one of these distributed memory machines. And it's called Global Address Space. And again, a program consists of a bunch of named threads, and usually, they're fixed at startup time, so you may have 64 or 1,000. And so here's a picture of it. And each one, again, has some local data. So the variable I in your loop from I equals 1 to n, that's guaranteed to be private. Only you can touch it. Doesn't cost very much to get it. And those are declared private. And then you have some other variables that are declared shared. They also live in your local memory, right? Because there is no shared memory anymore. But they're declared shared. And that means that, and everybody has to agree to declare them shared. And so that means that you can refer to data on somebody else's processor. So if you declare the array S to be shared, and processor 0 owns S0 and processor 1 owns S1, then processor 0 can just go and say, S0 equals 7, S1 equals 32. And what happens when you do that, what the hardware does is it recognizes that S1 is a shared variable, it's not on your processor, and it automatically generates a message. The compiler and the hardware, without you having to do anything, will generate the message and go tell processor 1 to set S1 to be equal to 32. So it sort of behaves like shared memory, and of course it's more expensive to do that, but it's built on top of distributed memory hardware. So, and there are a number of examples. Some of these languages have been produced here. UPC, your third programming assignment will be in Unified Parallel C. Titanium is another local project. CoArray Fortran was done somewhere else. They have their user communities. Some people really like to do it this way because it's very, you can write a parallel program much more easily than an MPI where you have to do all this sending and receiving, but you still have to pay attention to what's local and what's remote. If you spend a lot of time reading and writing somebody else's data, it will still go slowly. I mean, the hardware won't change that. It'll just be easier for you to express that. So here's what the machines look like. As I said, they look basically like the machines I showed you before. Hopper is an example, except now the network interface has more responsibility in order to implement these remote reads and writes. And so the way it's written, this works is the network interface now, without bothering the CPU, who's doing something else, can execute the read and write instructions from another processor. So if this processor says, please go set S sub 1 to 32, that network interface chip will talk to that one, and this guy will set S sub 1 to equal to 32. And processor 1 won't have to be bothered by it. Now you can imagine you'll get all kinds of race conditions if you're not careful, right? All those race conditions can still happen, but it's easy to program. You can just go ahead and do it. And so, in fact, so these are called one-sided communication, right? So if I say S sub 1 equals 32, processor 1 doesn't have to get involved, right? It's all handled by these network interface cards. And if I want to get the value of S sub 1, I can say, local variable equals S sub 1. Again, the network interface cards talk over the interconnect, and processor 1 doesn't get interrupted to go get the value of S sub 1. So that makes it easier to do this one-sided communication. So, and so in order for this to not have multiple copies of S sub 1 which are all inconsistent with one another, it typically doesn't cache local data, right? Every time you refer to it, it's got to go get it to make sure it's the cleanest, most recent value. Okay. So that's the end of shared memory and message passing and global address space. So that's how far we've gotten in this agenda. And now it's time to go to the next programming model and the next set of machines, which is data parallel. Think the GPU on your laptop. Okay, are there any questions about the first 2.5? Yes?
So in the kind of pure shared memory machines where you have, one box and maybe you have a couple processors, right? There's there's a method that you were talking about for making sure they're coherency, right? Versus in the
right. So whenever you refer to data, it will go over the bus and make sure that whenever you write a location, it will go over the bus and make sure that the other person's cache is aware that the value that they might have, the copy they might have of it, is now out of date.
Right. So in the distributed shared memory, sort of syntactic sugar that lets you do that stuff, why does it always ask for the new one as opposed to having some sort of background process that just verifies coherency?
So there could be some special stuff going on inside the network interface to do that. It might keep some tables, but I think it's designed to scale, and so that having those tables does not scale. But I'm not going to pretend I know every last recent hardware innovation in the network interface card world. So, does anybody else have a comment on current UPC implementations and GasNet? Right. The name of the library that does all of this putting and getting in one-sided communication is called GasNet, Global Address Space Network. And so I invite you to Google it. It's a local project, and you can see what the latest implementations look like. And you'll use it in Homework 3. Okay. So now we're going to go to data parallel. And so the programming model is very simple. Just think MATLAB. A is an array, B is an array, C is an array, and you write one line of code, and it adds all the entries in that array to that array and gives you that one, right? So that's the simplest, another very simple programming model that a lot of people like. And of course, we can't just do it to entire arrays all the time. I want to have the freedom, for example, to take the first half of the array B and add it to the second half of the array C. And so I need to be able to define in this programming model subsets of the data, of a data structure, and do operations on them. And the nice thing about this is that all the communication is implicit. If I write this and the entries of B and C are not on the same processor, then that's all hidden from me, and the machine will move everything around for me. And it's all inherently synchronous. So this line of code executes completely. You write what looks like sequential code. Even though this is parallel, this line of code finishes, and then you execute the next line. So there's no chance of people having different copies of the data that are not coherent with one another, because there really is only one program that's executing where you express all the parallelism. And of course, not every program can be written in this format, but when it can be, it's very convenient. And so the problem that we had, where I had an array A of data, and I wanted to compute a function of every entry, so f of a1, f of a2, and then compute the global sum, it would be 3 lines of code in a programming language like this, which is, I initialize my array of data, I compute f of a, that automatically just applies f to each entry one at a time and gives me a new array. And typically there's a built-in sum function in these kinds of programming languages which does a big reduction and reduces all those arrays to one sum. And so this is very convenient for programming if your problem happens to fit in this paradigm. So what does the hardware look like? So let's talk about the machine models that people have built to make this run fast. So the generic term is SIMD, or single instruction, multiple data. So one add instruction, which then does it on many, many data sets, many values of the summands. And so what you can think, the way these machines work is there's a single control processor. That's the only one that knows there's an instruction which says add up a bunch of numbers. And then there's a whole bunch of individual tiny processes. You could think of these as adders or multipliers or whatever. They're not smart enough to have their own instructions. They have to wait. They're slaves of the control processor. They just do what the control processor says one step at a time. And they have their own local memory. They may have their own network interface, but they're all doing what the control processor says to do. And there were a bunch of machines that were built a long time ago, the Connection Machine 2, MassPar, that were designed this way. They're all a bit of history now. And the programming model can be implemented by the compiler. When you write MATLAB and you write A equals B plus C, the MATLAB interface understands what you mean by that. And in general, now they have to map that to multiple processors. So if you're taking an array of size n, A and B, and you have P processors, it has to divide up the data among those P processors. And sometimes that's easy for the compiler to do, and sometimes it's hard. There was an attempt, just one second, high-performance Fortran, but making compilers smart enough to recognize all the parallelism in your code has been an open problem for a long time. So, question?
So how does the communication happen between the control processor and the slave processors?
So each control processor says, please execute. It sends the instruction stream to each slave processor. So along this wire, it's going to send, an add instruction, the same add instruction to all of them, or it may send, nulls to the others. Maybe your array is so short it doesn't need all of them, so it could only do a subset. And it will also probably send a pointers to which subset of the data to do it on, right? Because processor 1 and these two processors, these should be processor 1, 2, 3, should all be working on separate copies of the data. So it'll probably send the same instruction add, and then say different subsets. Okay. So that's an SIMD, and the simplest example would be on your laptop, your Intel chip. It has SIMD instructions which will add 2 or 4 or 8 numbers to one another at the same time. So this is all very small scale in that regard. So here's another example which was more important historically but disappeared for a while, and now it's coming back. And those are called vector architectures. And now the way these worked is that there was a single processor, as I said, and how was the data stored? You may have had a register, a vector register, which had 64 numbers in it. And when you executed an instruction which said, add register 1 to register 2, it was actually adding 64 numbers at a time to the other register, which also had 64 numbers. And it would also let you pick arbitrary subsets. You could pick any subset of those 64 and add it to the next one so that you could do more irregular things. So these were historically important. These were the biggest machines in the world in the top 500 list for a while. But they got overtaken by what are called massively parallel processors, clusters, because it was a lot cheaper to build clusters for a while. You didn't have to buy this special purpose hardware in order to run fast. Back then, going and buying a commercial network wasn't much slower than the special purpose stuff. But now, because of Moore's law and the processors are going so fast again, people are saying, well, now I want to take advantage of something special purpose. So it began coming back. So the largest machine in the world, again, for a while, was the Earth simulator. That was an NEC machine, an SX6 that had, millions of ways of parallelism. And as I said, it's also happening at a smaller scale here. And it's in your GPUs. So let me just show you another picture here. I think I've already sort of said this. If a single instruction will typically take the value of one register, add it to another, and give you a single answer. Now you have a vector register, which has 32 entries, a second vector register, which has 32 entries, and your adder adds them all in principle simultaneously. And so it does that by having things called lanes or pipes, so that all of this sort of gets pipelined through in that pipeline parallelism stuff that I told you about before. And for example, if I have 2 lanes, all of those can happen in parallel. OK. So let me just show you a picture of the Earth simulator. And this is an interesting historical machine. It was number 1 in the top 500, I think, for 5 runs in a row. So they sort of invested the Japanese government an enormous amount of money because they wanted the biggest machine in the world, and they actually held the record for quite a while. It was 2 basketball courts in size. So it actually filled up quite a bit of space. Everything was custom. And I remember working on a committee writing a report on supercomputing. And when we were looking at this machine, we realized that the latency to send a message from one side of the machine through all the wires across the 2 basketball courts to the other, if you just said, how long would it take at the speed of light to follow all the wires, it was 1/10 of a microsecond. That was the latency across the machine. And then we asked, well, what's the latency if you actually call the send subroutine? And it was not much slower. It was 10 microseconds. It was a factor of 1,000 off from just the speed of light. But it was clear at that time that they were getting close to hardware limits. That the speed of light is a real hardware limit. And so the question is, how do you at some point, algorithms that were sending too many messages were going to hit these hardware limits. So that sort of set off a lot of research in how do you minimize communication, which we will get to later in the semester. Yes?
Did they really build a...
You should leave it on.
Did they really build a fully connected crossbar?
So it was hierarchical. And so at certain layers, it was fully connected. And then above that, there were more connections. But it wasn't everybody to everybody. But one of the reasons they had a special building for it and everything else was because there were so many more wires that they invested in. So that the communication, they tried to minimize the amount of hops in the network. Right? So this was an investment that probably will not be repeated very often. OK, so we have now finished all of these sort of basic vanilla architectural types. And I want now to go on the last one, which is saying that the biggest machines today are mixtures of all of these. They're hybrids. And that's just the reality we have to deal with. So the simplest things, the shared memory processes, the multi-core chips in your laptop, they're the building blocks for larger machines with the network. An old-fashioned name for it is clumps. Clusters of SMPs, but Hopper is a good example. So Hopper has, has thousands and thousands of nodes, but if you look inside each node, it's a 12-way multi-core, right? So that means how do we program these things? So there's 2 ways to do it that you can imagine would be very easy, because the machine is partially shared memory inside a single node and partially distributed memory. You could ignore the fact that you have this hierarchy and just treat the whole machine as flat. And so that means use message passing. Every one of those 12 cores, even though it's really cheap to talk to their neighbors, will still be a separate MPI subroutine. And it will do sends and it will do receives, whether it's going all the way across the machine or just a little ways across the chip. And people have tried to rebuild MPI so that it's cheaper, so that it kind of knows if you're talking to your neighbor or not. But this still is not, there's still a lot of overhead to call that subroutine to talk to your neighbor. And so the other option is to write a hierarchical code to match your hierarchical machine. So you'll write for example, an a shared memory program written in some language like OpenMP or pthreads that we'll talk about. That runs on a single 12-way node. And then that will look like one MPI subroutine. So inside it'll be doing 12-way shared memory parallelism, but it'll have one MPI process that talks to all the neighbors. And so if someday they have a more complicated machine, and they do now, you may not only have these 12-way nodes, you may have a few GPUs hanging off the side. Then you need a third model, right? You have to program the GPUs in yet another language. And so right now there are a few ninja programmers who actually take advantage of all these different levels of programming for sufficiently important problems, like the top 500 list, and a few others. But it's an open computer science problem to make it possible to program all these easily and get the full speed out of all the different layers. So that's why there's no choice today but to learn shared memory programming and the distributed memory programming, and maybe you'll need to use both for a particular application. So that's what the hybrid machines look like. And as I said, people are trying to make the programming models hybrid. So there are some attempts to invent some new languages that will deal with this. So the DARPA HPCS, High Performance Computing Program, invented a bunch of new languages, and some companies signed up to do it. I'm not sure those languages are widely used yet, but they try to have a global address space, so it kind of looks like shared memory. But you have to know that sometimes it really is shared memory and it's fast, and sometimes it's going through the network interface card and going somewhere else. So it can't completely hide the fact that some data is expensive and some data is cheap to get to. And so anyway, this is what Hopper looks like too. Now, I haven't said anything about GPUs or clouds yet, and I just want to have one slide because we're going to have 2 lectures later in the semester, one just about GPU programming because it is so important, and one just about cloud programming. And I just wanted to say, where do these kind of fit in this framework, in this hierarchy? So GPU is basically data parallel, or SIMD, or vector. And so, and in particular, the GPUs work best when you can think of thousands or tens of thousands of things to do at the same time and do the same operation on them. And they were invented, GPUs stand for graphical processor units. They were invented for drawing pictures in your screen, and each pixel you could think of as a separate program, and you're doing the same thing at each pixel, and there are a lot of pixels. So it was easy to think of a lot of parallelism. So these machines were originally invented for doing that. And then they realized there was a big market in other kinds of computing, and they made them easier to program, and now people use them very widely for doing simulations of various kinds and not just drawing pixels. And we will have a lecture later by a former graduate student who now works at NVIDIA, who's one of the innovators in this field. We'll talk about CUDA programming, which is the special C-like language that you need to program on GPUs from NVIDIA. And of course, now a lot of other companies produce GPUs too. And so the community, again, has been trying to come up with a standard way to say, how do I program these things so I don't have to change my language all the time? And the attempt is called OpenCL. And it's a work in progress. And the lecture later will cover both languages, CUDA and a little bit about OpenCL. So then there's cloud computing. And so where did this come from? This was originally, companies like Amazon and Google had warehouses full of thousands of computers that they used for their web search. And then they realized there was a market to let they needed to program efficiently themselves. And then they realized that other people were willing to pay money to use these huge facilities. And so the first way that they made available to program it, so this is all very distributed memory, was something called MapReduce, which is simply do something embarrassingly parallel in all the processors. That's a map, compute f of a in my example, and then reduce was compute a global sum, right? So much of web search can be reduced to operations like that, where you look at all these web pages independently, and then you do a reduction to find the most likely web page that you want to tell the user about. And so now, for a few cents, per minute, I don't know what their prices are lately. You can look at their web page. You can just put in your credit card and program on 10 to the 5th computers if your programming model happens to fit in this. And there's a lot of innovation going on now in doing things more general than embarrassingly parallelism. And there's a big lab at Berkeley and other places too that are inventing new programming models for this. And we will also have a guest lecture later in the semester on how to do cloud programming. And so all of these are fair game for class projects as well. Okay, so let me just close in lecture 3 before I go to lecture 4. And there's sort of several basic conceptual models. I talked about shared memory, where everybody's, location 37 in memory means the same thing to every processor, even if you have to go far away to get it. distributed memory, where everybody owns their own private memory and they have to send messages to one another in order to agree on sharing data. And then data parallel, where one instruction, in principle, can add a 1,000-length array to another 1,000-length array with one line of code, A equal B plus C. And of course, real machines are hybrids. And all of these machines, running them quickly, depends on the same three problems, which is try to get the problems as independent as possible so they don't have to talk to one another and say, are you done yet? Are you done yet? Have them be about the same size, so it's all load balanced, so each processor finishes about the same time. And have good locality. That means they should refer mostly to their own data so they don't have to spend all that time going over a network to get to somebody else. And everybody, these are the same three problems for all of them. They're just addressed in different ways. And so the next lecture, which I'm about to begin, is going to be how to recognize opportunities for this. They come up completely naturally in applications. Applications have natural independence, if you think about them the right way. They have natural load balance, and they have natural locality if you in certain kinds of simulations. So I'm going to show you a bunch of patterns now about where these come up. So let me just take a short break to tell you about yourselves. It's always fun to look at the class makeup, and someone else just joined today, so that person's missing from here. So as usual, we have about half computer science or ECS, and half from everybody, all the other departments on campus, including, well, you can see the list there. So who's the business student? Are you in the room right now? So I had another business student in this class a few years ago, and his project, which actually turned into a master's project, was very interesting. He looked at how companies benefited from whether their software that they needed to use to run the company, how parallel it was. And he sort of could measure companies on the basis of how well they were able to take advantage of the multi-core revolution. And so that turned into an interesting master's project, and he had did a PhD in a separate project. So there's all sorts of interesting ways you can make up projects, and there's a bunch of undergrads in here too, as is common. So are there any questions while I now switch to sort of higher in our stack, looking at high-level applications, and asking how they automatically they generate lots of independent problems of about the same size with good locality. Yes, question, and microphone. Maybe you can do a chain to hand it back there.
So you mentioned that basically the processor control is a hierarchy of locality. So in the hybrid models, like in the array, you have the cache, you have the shared memory, and you go up and up and up. And
yes,
I'm assuming
and it gets more expensive the farther you go.
As you go from bigger node to bigger node, you got a gigabit or whatever. Is this interface open to actual programming, or does every company have to write its own kind of hierarchy of how an MPI correlates to where to go, kind of stuff?
So some of it, once you're on the node and it's a cache, then the hardware automatically decides for you which level of cache it's going to put your data in, because it has these rules that it's built in as to, if you've used it recently, I'll keep it in the highest level cache. And if it fills up, I'll push it down into a lower level of cache. And so you sort of have to have a simple mental model of those rules, which can be kind of complicated to write your program correspondingly. Some machines, so the Sony PlayStation had a different kind of memory where you were responsible for moving data into the cache, the fast local memory, and putting it out again. So you had to decide what you needed locally and putting it back. For MPI, you get to decide pretty much everything. You decide what's local because you've written a program, and whatever that program is, it runs on a single copy of its memory.
But for example, if I have a 64-core machine, and say there are two machines, and I ask for 65 cores to my program, will I run as slow as the transfer between the machines?
So there are different allocation mechanisms. So even on a single chip, you can have a hierarchy. And we'll have a lecture later where someone tried to very carefully tune some sparse matrix algorithms, taking into account that there were 4 processes, 4 L1 caches, 2 L2 caches, and he had to get that hierarchy right to make sure that all of the, to minimize the amount of data movement. So that required sort of careful programming and sort of pinning memory to certain caches, and knowing that which subroutine accessed which caches work. It was very low-level programming, but it made a big difference in performance. Hopefully, most of the time, people don't have to worry about it. unfortunately, it still can have an impact. Another question?
So what's the biggest difference between vector machine and SIMD machine?
So, this is a good question. It's asked every year, and to some extent it's notation. So vector machines sort of went away for a while, and they were considered old-fashioned. And when it became a good idea again, people didn't want to use the name vector because it had all these old connotations. And so, in fact, if you look at Patterson and Hennessy's textbook, in their section on GPUs, they have a whole section which says, here's the terminology in the GPU, here's what it was called in vector machines, it's really the same set of ideas. Yeah. So, yeah. Oops. So does any more comments? These are good questions. So now, finally, lecture 4, which is, again, going to last into the next one as well. I'm going to talk about how parallelism and locality naturally come up when you try to do simulations of very commonly arising systems. So I've made the point so far that finding lots of things that you can do at the same time, parallelism, and working on data that's local, so you don't have to go talk to data that's far away, they're both critical to performance. And so the good news is that many real-world problems that presumably you guys want to write simulations of naturally have parallelism in locality. And I'm going to give you some high-level reasons now, but give you lots of concrete examples. So many objects in the real world operate independently of others, right? So I'm independent of you, I'm talking and you're doing something else. If you have a bunch of billiard balls which are rolling around, each one is independently operating under F equals ma until they get close enough together to collide. It's just a natural phenomenon in the way the world works. The other thing is that objects often depend much more heavily. They have to communicate a lot more with other objects that are close to them as opposed to distant objects. So again, if you imagine billiard balls, it's not until they collide, until they're really close together, that they actually have to communicate and know what to do. But if you think about particles moving under gravity, they depend much more on the nearby particles than they do on particles far away, and we can take advantage of that. In particular for gravity, so imagine I want to compute the force of gravity on the Earth, because I'm going to move it around in some simulation. I have to pay very close attention to where maybe the moon is and where the sun is. But if I go out in the sky and look up and I see the Andromeda Galaxy, it's a little white dot, there are billions of stars in the Andromeda Galaxy. Do I need to have a term in my gravity sum for every one of those billion stars? No. It's perfectly fine to approximate the Andromeda Galaxy by a single point mass at its center of gravity. And from the Andromeda's point of view, the Milky Way looks the same. It can approximate the Milky Way by a single point mass. And so by taking advantage of that in a recursive fashion, we can reduce the cost of doing gravity simulation where everybody depends on everybody from n squared to n. So that's an enormous improvement that we'll talk about as time goes on. So we're going to do that as much as we can for all of these different things. So then, when you actually write down sort of a scientific model with a mathematical model that you're going to do the simulation, that can introduce even more parallelism. So for example, if you take a problem that's continuous, billiard balls moving around, time is continuous, but you're only going to simulate it at discrete time steps because that's what the algorithms do. And so that's going to minimize the amount of dependency. If you only need to go from time t to t plus 1, then that's going to limit how many objects you can possibly have to communicate with because things can't move that far in just one time step. So we're going to take advantage of that as well. And many problems exhibit parallelism at all these different kinds of levels. So what I'm going to do is divide up all the simulation problems that there are into 4 different kinds. And they're going to be the same sort of tricks that come up in parallelizing each kind. And they're going to be sorted kind of in order of how discrete they are. And so the first example is where everything is discrete. So time is discrete, the objects are discrete, the rules are discrete. So these are called discrete event systems. The simplest one, if you ever remember the Scientific American articles, is the game of life. So you have an array. Each array has a certain population in it, and depending on the population of your nearest neighbors, you will either, the population will change at each grid node. So there's a discrete set of grid nodes. There's a discrete time step, time t equal 1, t equal 2, and there are rules for how many how many guys are in this cell at time t and how many are in the cell at time t equals 1. Manufacturing systems, if you have objects going down an assembly line and they're being taken on and off by different manufacturing units at the same time, you want to write a simulation of that. That's also a discrete event system. Finance, I mean, those are transactions. Those are obviously discrete events that happen. Now, circuits are a little bit more interesting because circuits are going to be simulated in all sorts of different ways. But if you think of a digital circuit, it has gates that are either on or off, and there's a finite number of them, and there's a clock, saying what happened, what's the state of the machine at time t, t plus 1. That's all a big discrete event. Depending on which other pieces of the circuit you're connected to, you will decide are you a 0 or a 1 at the next step. And finally, there are games, old ones like Pac-Man that you may have played. So the next level of simulation, where I make it a little bit more continuous, is particle simulations. And so now time has become continuous, but I'm still going to discretize it into time t equals plus 1. The particle positions are continuous, but there's still a discrete set of particles, right? I have a finite set of billiard balls that are moving around, or a finite set of galaxies moving under gravity, or a finite set of atoms. And so what I'm going to do at every time step is I'm going to make up some rule that says where am I at time t, where am I at time t plus 1. And so this is gravity, this is bouncing balls, this is maybe rules like let's see, there's both electrostatics and other kinds of properties that decide whether this atom is how connected it is with a bond to its neighbor and how fast it's going to move. Now, circuits can also be done at the particle level in case that you want to think of individual electrons moving along wires, and people do actually simulate circuits at that level. And finally, there are yet other kinds of games, slightly more modern. Pinball is an example. So the next level of simulation, I make it even a little bit more continuous, and these are called lumped variables. So I have a finite set of variables, but each one is continuous, and it depends on a bunch of continuous parameters. So its neighbors, some time, and so forth. And basically, this is ordinary differential equations, or ODEs. So if you've ever had a class on that, this is a very common pattern. It comes up over and over again. And it's a little bit more general. It's not only ODEs, but it's ODEs with constraints. You may have some other constraints that go along with it. That's exactly how circuits are simulated. So there's a famous circuit simulator called SPICE that was invented at Berkeley that represents a circuit by resistors and capacitors and wires connecting them and voltages and currents, and it writes down a system of ODEs with constraints, and it solves it. That's widely used to design circuits. Chemical kinetics, again, you have equations which say the rate of change of the quantity of this particular quantity depends on all the other quantities in the chemical reaction. F equals ma, structural mechanics. Will this building fall down in an earthquake? You write down F equals ma for every little girder and solve that. And then there are even more interesting games that come up. So in this case, this was released a few years ago. And whenever Darth Vader smashes something, it's doing real-time parallel finite element simulation, so it actually gets the smashing right. So it looks as realistic as possible. And I'll show you a video of that next time. So finally, the last level where absolutely everything is continuous, time, space, all the quantities you're interested in, and another word for that is partial differential equations. And these come up in the heat equation, right? Temperature is a function of both position and time, and it depends on all the quantities around it and the temperature there. Elasticity, how things bend. Electrostatics, so Maxwell's equations. Now, finance comes up again. I had it earlier. And in this case, it's the Black-Scholes equations, just to name one. That's a PDE that tells you the price of derivatives that won the Nobel Prize in Economics in 1997. So that's yet another source of PDEs. If you want to do a circuit at a very low level and know exactly where everything is in a piece of silicon, you would write down a PDE, again, Maxwell's equations inside that piece of silicon. Medical image analysis comes up. And in Terminator 3, this is yet sort of one more level of entertainment. This was a movie that was released a few years ago, and it did very detailed finite element simulation of various fluid splashing, not just water. And so whenever our former governor smashed something, it did all the physics right. So that's another example. And I should say that there's another interesting difference between Star Wars, The Force Unleashed, and Terminator 3, The Rise of the Machines. Here, all of the interesting technical development was done at Berkeley, and here it was all done at Stanford. So anyway, so I will only show you the videos from the Berkeley development there. So of course, any given phenomenon can be modeled at multiple levels. I think I put circuits. It's all 4 levels, and depending on the level of detail you want, you may have part of the circuit simulated one way and part of the circuit simulated another. And here's a pointer to the video I'm going to show you later of Darth Vader et al. So let me just give you an example for circuits, since there are a fair number of EECS folks in here. So you can simulate circuits at many levels, and here I have them sorted from most discrete to most continuous. Here are the individual units of objects that appear in the simulation. And here's some examples of commercial software or research software that people use to do the simulation. So at the most discrete level, and let me just sort it from discrete to continuous, you have individual instructions that are executed in the machine. In that case, the primitive is add register 1 to register 2, and that's a perfectly reasonable level to simulate what your program is going to do. Now, if you go down to one more level of detail, you would go cycle by cycle, because one instruction is broken up into many, many little steps. And in that case, you might look at the functional units, and I had a picture of that. So you might separate out the adder from the registers from the memory unit and do those, ask what they do step by step, but it's still quite discrete. Below that, you can go and look at individual registers and counters and muxes, and that's written in a language called RTL. And finally, you can go down to gates, where all you have is zeros and ones, flip-flops, memory cells, ands, and ors. And again, but it's still all discrete. Things are happening in one state. And all of these give you different levels of information that people want. And you can go all the way down to transistors, on and off, if you like. And now those are all discrete. We get to the continuous level when we have circuits, and we write down Kirchhoff's laws, and we, that all the electrons going in have to equal all the electrons going out of any particular junction, and you have equations for resistors and capacitors and inductors and so forth. You write down a big complicated system of ODEs with some constraints, and that's simulated using SPICE, and that's widely used. And then, of course, you can do it all at the device level. So here's going to be the outline of the rest of this lecture, which is going to go not just be today, but next time. I'll start with a discrete case, move on to particle systems, then do general ODEs, and then do continuous, talk about PDEs. And in each case, I'll say where parallelism arises naturally, why you should, patterns that come up over and over again, and how locality comes up naturally. Okay. Now, in order to teach this stuff, without necessarily knowing all the physics of each example, because the patterns are kind of independent of the physics, we've written over the years a bunch of model programs for a very simple simulation called Sharks and Fish. It's on the web page, and it's basically a bunch of rules for a bunch of sharks and fish and possibly sharks living in an ocean. There are rules for how they swim around, the current pushes them around, how do they breed, they eat, how the sharks get attracted to the fish and eat them, forces in the ocean. And there's very low level, very made up kind of game-like rules for all of these things. And we've shown how to implement it in a whole bunch of different languages. So we have implementations in MATLAB, which is just very few lines of code. We have shared memory implementations in pthreads and OpenMP. We have distributed memory implementations in MPI. And these are sort of baby problems that illustrate all the different simulation problems that come up. And so you're welcome to look at those. We're not going to assign these for homework. The homework has similarities with them, but these are sort of available for you to look at. And so here are the different sharks and fish examples. The first one is that the fish ignore one another. They just move continuously, subject to F equals ma and the external current in the ocean. That's the simplest thing you can imagine. It's embarrassingly parallel. Then we throw in gravity. Fish attract one another. They form schools, and in addition, the ocean pushing them around. And so that's, I'll show you that code a little bit later, because it's good to teach with. So those are continuous, if you like. Then we have the game of life. So fish are born or die at each grid cell in the ocean, depending on how many of their neighbors are populated. And then we throw in some sharks, and of course the sharks are attracted to the fish are not attracted to the sharks, and there are rules for who eats whom and so forth. So anyway, there's sample code for all of these things. So now let's go on to discrete event systems. And as the examples I told you before, systems are represented, there's a finite set of variables, and the set of all the variable values at any particular time is called the state. So if you have a digital circuit and there's a bunch of gates in it, each one either 0 or 1, the lists of all those zeros and ones at any particular time is called the state. And then there's a rule which says if I know the state at time t, there's a function, a transition function, which will tell me the state at time t plus 1. So everybody gets updated depending on its old value and its neighbor's old value. Now there are two ways this system can march forward, and they correspond to two different styles of parallelism. One is called synchronous, and the other is called asynchronous. So synchronous, the easiest thing to think of as a computer, there's a clock. And every time the clock ticks, you update everything. And that's also called a state machine. But even maybe more common and interesting is asynchronous, when you don't bother changing your value until somebody who's connected to you says it's time to change. And so you have to wait for events to occur in your neighbors and to maybe tell you that they happened, and only then do you change your value. And of course, once you change your value, that can propagate and other ones can change. And this is also called event-driven simulation. And these two have rather different styles of parallelism, and which come up over and over again, which is why I'm telling you about them. And the sharks in the game of life, one of those sharks and fish games is a typical example. So let's look at the game of life in particular. So this is going to be the simplest case. It's all synchronous. So there's going to be one grid where each value stored there is, is this grid cell, dead or alive? How many, it's an integer at each grid cell value. And so what I'm going to do is I'm going to have two copies of the grid, the old state and the new state. And at every time step, I'm going to read the old values and write the new values. So if the old grid is at time t, the new grid will be time t plus 1. So that gets me ahead 1. Now, how do I get from t plus 1 to t plus 2? I just swap the labels old and new. And I take all the values in the new, I read them, and they update the old. So I sort of ping-pong between these two states. And so I only need two copies of the data to march forward. And so what's true in the game of life, and what's true very commonly, is that what's the rule for each grid cell? How does it update itself? It only depends on its 8 nearest neighbors. So north, south, east, west, and the 4 corners. And so it only needs to sort of communicate to get data from its nearest neighbors, a total of 9 cells. And so at each time step, I have to get 9 numbers, compute some function of them, update my value. And so the question is, how do I parallelize that? I have a square grid. So this grid here represents my grid of numbers. And I have 9 processors. What's a perfectly natural way to assign the work of each grid cell to a processor? It's called domain decomposition. That's the word for it. I'm going to divide the physical domain. My array is a square grid. Think of that as a physical domain. And I'm going to assign some contiguous chunk of grid cells to each processor. And a perfectly natural way is to divide it up into squares, right? We'll come back later as to whether that's good or not. So processor 1 owns all the grid cells there, is responsible for updating them. Processor 2 owns all the grid cells in that square, updates them, and so forth. So what's the code look like? It's very simple. I'm going to repeat until I'm done simulating. So each of these updates, each inner loop does 1 time step. Now, what I'm going to do is processor 5 has all the information it needs to compute local data, as long as it doesn't need any data from processors 4, 8, 6, 2. So compute locally to update the local system. So if I'm in the middle, and most guys are in the middle, my 8 nearest neighbors are also stored in the same processor. Then I wait till everybody's done. I do a barrier. That's one of these subroutine calls that says, let's wait till every processor is finished. So now, if I need to update a value that's on the border, and so I'm in processor 5, but my neighbor's in processor 6, I now have to exchange state with the neighbors. So at this point, processor 5 and processor 6 exchange all the information about cells right along that border. Processors 2 and processor 5 exchange information about everybody along that border, and so on. And then, once you've done all those sends and receives, you finish your updates. You update everybody else, so you've now completely updated everybody that you own, and you just keep repeating. Okay, so that's the high-level code that does it. And so why is this? This is naturally parallel. I have 9 processors. I've given each one an equal amount of work to do, so it's load balanced. So because each cell takes an equal amount of work, and each of these squares has about the same area, so that's the load balance part. And so, and I don't have to communicate very much, because the data that I need is my nearest neighbors, and most of the guys here, their nearest neighbors are also stored in the same processor. It's only somebody who's on the border So the question now, the optimization question is, I've picked squares, but there's an awful lot of other shapes I could have picked. How do I pick the shapes of these domains? What subset of this whole big array should processor 1 own to be load balanced and to minimize the amount of data moved, minimize communication? So for this square mesh, the answer is very simple, and it's going to be much more interesting for harder simulation problems, but let's get it right here. So let's suppose I have an n by n mesh, and let's suppose I just need my 4 nearest neighbors, north, south, east, and west. And so here's a picture. Here's my 18 by 18 grid. Each grid point is a grid cell, and I need to talk to my 4 nearest neighbors in order to update myself. And let's suppose I have 9 processors. So I need to divide this 18 by 18 grid evenly for load balance among 9 processors. So let me show you 2 perfectly natural ways to do it. So here I've indicated by colors which processor owns which grid cells. So the first processor owns the first 2 rows, the blue processor owns the next 2 rows, and so I've divided up everything evenly. And so this seems perfectly natural. Everybody owns an equal amount of data, and everybody just talks to their neighbors. So there's that picture. And then here's the one I had in the previous slide where everybody owns a square. And so the natural question is, this one looks like it's easier to program. This one is a little trickier, but so why would I choose one versus the other? So what I want to do is ask, because they're both load balanced, they don't disagree there, everybody has an equal amount of work to do. I'm going to compare them based on how much they have to communicate. How many messages have to go from the red processor to the blue processor in order to update his values? So what I'm going to do now is observe that I can count that by just counting the number of edge crossings. How many edges connect one color to a different color? Because every one of those edges represents a word of data that has to move. So all I'm going to do is count the number of edge crossings between different colors. And it's pretty easy to do. For a general n by n mesh divided with p processors, I'm going to have n edges there, n edges there, n edges there, n times p minus 1 altogether. And if I do the same counting exercise over here, and I count all those edges, and all those edges, and all those edges, it's still proportional to n, but now it's proportional to the square root of p, which is a whole heck of a lot smaller. And so this is the one that wins for this simple example of a nice mesh where you just talk to your neighbors. And so the principle we're going to take from this, we're going to apply to the general problem, is that minimizing the communication is equivalent to minimizing the surface to volume ratio of each piece. So the volume, actually area, is the same for all of these. It's n over p. And what I want to minimize is the surface, or the perimeter, because the length of the perimeter is telling me how much communication there is. And this has a better surface to volume ratio than that. So in the plane, which shape actually truly just perfectly minimizes the surface to volume ratio, or the perimeter to area ratio? A circle, a disk. Yeah. Unfortunately, you can't tile the plane in a disk, so this one works better. So there's actually a surprising variety of different shapes that are going to turn out to be useful. Okay, so let me say how this generalizes past nice regular meshes. So a general problem is not going to be just talking to your 4 nearest neighbors. You can have an arbitrary connectivity. If you build a circuit, you put in the wires wherever you want, that's going to indicate who talks to whom, and you can have an arbitrary graph. So graph theory is one of those languages we're going to use throughout the semester. So what's a graph? There are a bunch of vertices or nodes, and they're connected by edges. In the case of a real physical circuit, the nodes are resistors and capacitors and stuff like that, and the edges are actually wires. And so what I want to do is figure out how to divide up that circuit or that graph so that it's both load balanced and there is few edges connecting one partition as another. So, and that question is called the graph partitioning problem. So let me just show you an example here. So here I have the same graph on both sides, and the blue nodes are the vertices, and the edges are the wires. And I have 4 processors, and what I want to do is assign these 8 nodes to 4 processors so that everybody is load balanced, everybody gets 2, and minimize the number of edge crossings. How many edges cross from one processor to another? Because that's the communication. And so here are 2 simple natural possibilities. And if I just do the counting, here the number of edge crossings is 2 plus 2 plus 2, that's 6. And here, count them all, it adds up to 10. And so this is the winner. And here I can sort of do it by vision. But what if I have an arbitrary graph? where it's not nearly as regular as this. It turns out that's a famous problem in computer science and mathematics. It's called the graph partitioning problem. And it's something called NP-hard. So how many people know what that notation, NP-hard, means? OK. So what NP-hard means is this problem is so hard that the best algorithms that anybody knows to solve it are exponential, like 2 to the n, in order to solve this problem, to find the best partitioning that both balances the load and minimizes the edge crossings. And if you could solve this problem faster, like in n squared or n cubed, you could solve this enormous long list of other incredibly hard problems nobody knows how to do. So this is sort of one of those standard hard problems that's as hard as anything else in computer science. So that means we're not going to do it. We're going to settle for a cheap approximation. We don't have to do it perfectly, right? We just want to do a pretty good job of minimizing communication. And there are lots and lots of ways to do that approximately, and we'll have a later lecture on that. But so this is one of those standard problems that come up over and over again, and they're well-established subroutine libraries and algorithms that do these approximations for us. OK. So here is another example of simulation that illustrates why we need to do it other than synchronously. So suppose I have some sharks and fish again. And so everybody's going to change depending on their neighbors. But now they're in this sort of loosely connected ponds, right? So here there's just this very skinny little path that connects these guys. And so if I just think about load balance, then the natural thing to do is just, if I have 3 processors, these are about equal areas, I'll assign 1 processor to each of these. And if I had lots and lots of processors and lots of ponds, I might just sort of divide it up by area. So everybody gets a certain number of ponds, and everybody gets about the work kind of area. And so the thing to notice here is that this processor can work independently for a long time. The chance that something is going to propagate up that skinny little channel is pretty small, right? So it's kind of a waste of time for him to look and see if something is coming along that channel every time step, right? This guy can just keep going forward very, very quickly. And that motivates another style of discrete event simulation called asynchronous simulation, where we don't have to stop and ask all the possible changes that occur at every step. So, so the point with this previous one is that if I have to stop and wait for something to happen here at every time step, it's a waste of time. And here, this guy is empty, and if I keep updating him, even though the nearest neighbor that could change him is very, very far away, I'm wasting a lot of time updating that cell too. OK, so what I want to do is take advantage of that by doing something called asynchronous simulation. So I'm only going to change my value when there's an event, when there's an update, new information from a neighbor, which could possibly cause me to change. So there aren't going to be any global time steps anymore. There's no clock. But every individual event contains a timestamp so that I know when it could affect me or not. And so the game of life in loosely connected ponds, for example, I wouldn't even bother simulating a completely empty pond because there's no messages there at all. And then when you simulate circuits, gates have delays. And so there's no reason to check until your neighboring subcircuit's actually done and sends you a signal. And if you're simulating traffic, well, the events are cars changing lanes, and there's no reason to bother doing something unless the car actually changes the lane. So asynchronous can be much, much more efficient, you can imagine, but it's also going to be a lot harder to parallelize in order to get it right. There are sort of natural ways to do it, and some of them lead to the problem that they can deadlock, and so we have to deal with that. And other ones naturally lead to the problem that you simulate ahead and you say, oops, I missed something, you have to back up. So both of those are standard ways of doing it. So let me just finish with this, and then I'll do examples next time. So there's 2 ways to do it. One is called conservative, and the other one is called speculative. And they're both used in practice. And in the conservative case, you're only going to simulate up to the point where you know you're going to get the right answer. So if all of your neighbors have said, I have finished simulating up to time step t equals 10, you are allowed to simulate up to time step t equals 10, but not to 11 because you don't know enough. So that's conservative. The trouble with that is it can easily get to deadlock. And I'll show you an example next time in the next slide. And so we need to have deadlock detection to make sure that everybody's not stuck waiting for their neighbor. Everybody's waiting for their neighbor. Nobody is willing to go ahead and take a chance. So we need to detect that. But it's used in practice. And the other one is called speculative or optimistic. In that case, you simply make a bet. I haven't heard, my neighbors haven't told me anything for a while. I'm just going to assume I can go ahead and simulate 5 more time steps, say, and keep going. But in case one of my neighbors says, oops, something happened a while ago, I need to keep a copy of my state 5 steps ago so that I can go back up and do it again. And so you may need to keep these timestamps, keep some old information around, and back up if necessary. And that's also widely used. And so next time I will give you examples of these and how they actually work. So that's a good time to stop. Are there any questions? OK. So did you guys want to say anything about logistics?
So I think a lot of you have probably gotten emails back from NERSC saying that your accounts are ready. It would be great if you could call them, get your password, make sure you can log in. If you can't, we'll email us and we'll help work it with you. And a handful of other people wrote their NERSC form in pencil, which obviously didn't scan. So I emailed you, and if I emailed you, it would be great if you guys could send me back those forms, bring them up to the Par Lab, we'll scan them and send them up there so that everyone can get set up on the machines before Matrix Multiply starts, because I'm sure you'll want all the time to actually work on the assignment. And on that Matrix Multiply assignment, the second point is please fill out the online course survey. If you haven't, we're going to use that to pair people up.
Right. So experienced, let's say, computer science majors and non-computer science majors. So all the teams can sort of go up the learning curve at a roughly equal rate. OK, thank you.